Everyone, thank you very much for the invitation to speak at this meeting. What I'm going to do is to look at how we can regard risk assessment as hypothesis testing and how that may help us to identify the data that we need to complete risk assessments. And just to say that my background is in environmental risk assessment, and mainly with single gene traits like Bt and herbicide tolerance. And I've also done a lot of work trying to get products approved in Europe. So with these caveats that I'm environmental risk assessor, I work a lot in Europe and I'm talking about single gene traits, I hope that what I say will have some general applicability to risk assessment for all traits. I think it's true to say that regulatory dossiers for GM crops are large and that they're growing. These photos are of colleagues of mine with the regulatory dossiers that they're about to submit. These are quite old photographs now, and the dossiers are probably much larger than these. And people have recognised this as a problem quite a long time ago. In 2003, for example, Mike Wilkinson and his colleagues were talking about regulatory gridlock. In 2008, Wendy Craig and her colleagues were writing a paper about the features of risk assessment. They were talking about competent authorities being submerged by excessively large amounts of data that may be of questionable pertinence to verifiable safety questions, which I think is a polite way of saying that we collect a lot of data that are irrelevant for risk assessment. I think one of the reasons that we collect a lot of data is that perhaps we think that the more data we collect, the better decisions we'll be able to make. And I think that hypothesis has been pretty much tested to destruction and found to be false. Often the amount of controversy and delay is positively correlated with the amount of data. The direction of causality may not be clear. We may collect a lot of data because there's controversy, but I think also collecting more data increases controversy as well. Here are some of the data that we collect to assess the unintended effects of transformation. Laura talked about some of these yesterday with regard to event selection. Here I'm talking about the data that we collect for regulatory submissions with regard to demonstrating the risks of using these products, both for human health and to the environment. And here are some of the things that we do: molecular analysis, transgene inheritance, compositional analysis, phenotypic analysis. We do feeding studies with poultry and rodents. We sometimes do non-target organism effects studies using plant tissue as a test substance, non-target organism field data. And these last two examples, these are really looking at unintended effects if they've not been triggered by lower tier data, perhaps on the active ingredient. In the past, I've done studies on the composition of soil microflora, soil phytotoxicity, plant demography in uncultivated land, and so on, all kinds of studies that are really seeking to investigate the unintended effects of transformation. And I should say that most of these data are from studies that compare GM and non-GM near isolines. And the questions I really want to raise are: what use are these data to us when we're doing risk assessment, and can we reduce or eliminate the requirements for them, given that they don't often seem to improve our decision making, which is really the reason we're collecting these data in the first place. Now, I want to start the investigation of these questions by perhaps posing it might seem quite an arcane question, but how do we know things? And one of my heroes, perhaps my only scientific hero, is Sir Karl Popper. He's the greatest philosopher of science ever, probably. And he was interested in establishing a logical basis for scientific knowledge. How do we demonstrate that we know things? What's the logical basis of that? And it's important when discussing Popper's work to remember this is the logic of scientific discovery. People think he's saying things about sociology of science or the psychology of science. He's not. He's simply trying to establish a logical basis for how we know things. And the view that he was criticising is really empiricism, and this is a very common view of science, or certainly was before Popper started to show why it was wrong. And the idea is that we clear our minds of any preconceptions and we go out into the world and we make observations, unbiased observations, and we collect these things together in our bucket of facts, and somehow these facts accrete into knowledge. So we're moving from specific cases, specific observations, to general laws. And Popper said this can't be right, because while the theory may be true, we can never prove that it is true. And the famous example that he uses is that of swans. We may have a theory that all swans are white, and we could observe millions, tens of millions of white swans, but that would never prove the theory, because you only need to observe one black swan, and that will show that the theory is false. So rather than knowledge being acquired by this empiricism, by inductive logic, what he said was it really is acquired by deductive logic, and he proposed this little framework for what's going on. And he said rather than starting with observations, we start with problems, and in seeking to solve those problems, we propose tentative solutions, and if we're scientists, those solutions are hypotheses. Then we seek to show that these hypotheses are wrong. We try to find what's wrong with them by doing tests, and he called this stage error elimination. This is where our observations come in. We try to see whether the predictions of our theory are in alignment with what we observe, and it's by improving our hypotheses, by rejecting those that are false and maintaining those that are not yet false. This is how we acquire knowledge. So knowledge is simply a collection of theories that we've not yet shown to be wrong. And what I'd like to do is to investigate whether this idea can help us identify those data that are essential for risk assessment. So if we apply Popper's metaphor to risk assessment, we seem to have this idea that more data equals better characterization of risk, and if we collect enough data, then somehow we can prove that the GM crop will be safe. So we make lots of observations of the crop, we collect them in our bucket, and somehow from those facts the safety or otherwise of the GM crop emerges. What I think we ought to be doing is trying to look for a deductive logic framework for this, if we believe that Popper's analysis is correct. And to do that, we really want to just firstly to say what do we mean by risk. I think it's important for what follows to understand that. And the definition that I think is most helpful here, and I've taken this from the Office of the Gene Technology Regulator Risk Analysis Framework, is that risk is the severity of some harmful effect multiplied by its probability. So high risk is a combination of high severity, the effects are severe, and they're highly likely. Low risk is that the events are marginal severity, and they're highly unlikely. And it's important to remember, other people have said this, but I don't think it could be said often enough, that harm is defined from our values. This is what we don't want to see happen. It's not established by science. These are our preferences. They're not facts. So let's use Popper's analogy, and we could say, well, let's say that a harmless effect of using a GM crop, that's equivalent to observing a white swan, and a harmful effect, we could say, well, that's the equivalent of observing a black swan, or any non-white swan. And so the statement that the use of this GM crop is not harmful is equivalent to a statement that all swans are white. And if we use that metaphor, then risk assessment characterizes risk by testing hypotheses of the kind that a particular use of this GM crop, use X of GM crop, Y, will have no harmful effects. And it's important to say that this says nothing about the acceptability of risk. We don't have to show that the GM crop will have no harmful effects for it to be acceptable. All I'm saying is this is the structure of what we're doing. This is a logical basis for what we're doing. And going back to the swan analogy, this shows that we can't prove safety. The best that we can do is to test and corroborate or falsify hypotheses about the amount of risk. So have this little scheme. The problem we're trying to solve is how best to assess risk. We set up our hypothesis about the use of this particular GM crop. Won't be harmful. We test the hypotheses by acquiring data, maybe existing data or new data, and that leads to risk characterization and decision making. So we may think, well, we've got a simple criterion here for identifying essential data. What we ought to be doing is testing hypotheses and not filling buckets. Fantastic. The problem is that, as Popper goes on to, it's always saying what he's doing is establishing a logical basis for science. What he's saying is this is how knowledge is developed. He's not saying this is how it ought to be developed. So in other words, what he's saying is that empiricism, filling buckets, that's impossible. It's not undesirable, it's just impossible. Because preconceptions, hypotheses, always precede observations. It's not possible simply to observe. If I told you to observe, you'd immediately say, observe what? You have to choose something to observe. This is an interesting website. Somebody who really loathes cricket, and he contrasts watching cricket to watching paint dry. And this chap here, he's watching his paint dry. But even that simple observation is testing a hypothesis. His hypothesis is that watching paint dry is more interesting than watching cricket. And this shows that we can't simply observe without any preconceptions, without any hypotheses. There's always a hypothesis. If that's true, then all data on a GM crop therefore must be associated with some hypothesis. It's often not explicit. It may just simply that we think they might be useful in some way, but we've chosen to observe those things rather than other things. And we can always erect a hypothesis post hoc to justify why we've collected those data. I do it all the time. If you want some tips, I'll be very happy to help. So lack of a hypothesis can't be a criterion for deeming data irrelevant. However, what we can say is that knowing that knowledge develops from hypothesis testing is useful for identifying data that are essential for risk assessment. They help us to identify relevant hypotheses. They help us to identify when hypotheses have sufficient corroboration. We may have looked for lots of black swans and not found them. Perhaps it's time to stop looking. And it identifies strong tests of hypotheses. Where are we most likely to see these black swans? Let's go there to look for them rather than somewhere else. So what I want to say really is that testing irrelevant hypotheses, testing hypotheses that are already sufficiently well corroborated, or weak testing of relevant hypotheses, this is what I mean by bucket filling. And I think certainly irrelevance and sufficiency are judgments. Weakness of a test, perhaps there's more objectivity there, but we have to judge when a hypothesis is irrelevant or it's already been sufficiently tested. These are not facts, like observing a white swan, for example. So let's look at irrelevant hypotheses to start off with. So studies of unintended effects almost always test a simple hypothesis, something like this, that some variable doesn't differ between a GM crop and its near isoline, non-GM isoline. And what I suggest is that this and similar hypotheses are irrelevant for risk assessment if there's no value of that variable that could indicate the potential for harm. So in other words, the hypothesis that the GM crop will cause no harm can't be falsified by measuring this variable. So this is the equivalent of asking the question, well, are all these swans different shades of white? As a risk assessor, I don't care. They're just white swans. And it's a slightly flippant comment, but a white swan is still a white swan, even if it has a different transcriptome, proteome, metabolome, or whatever. These are simply harmless effects. Regardless of whether they're different from each other, they're still harmless. So here's it's a table from a paper that some colleagues and I wrote a few years ago about this is a Syngenta event. It's actually alpha amylase. But these are some of the things we measure in compositional analysis. And the question I want to raise is, are there potentially harmful concentrations of all of these variables? And if there aren't, then don't measure the ones that would be harmful, at least not for the purposes of risk assessment. I'm not a good enough toxicologist or nutritionist to know that, but I wonder whether we could think of harmful concentrations of all of these things. And let's not measure the ones that we can't. And a bit stronger ground here in phenotypic analysis. This is the same event, and these are the things we measured. Again, are there potentially harmful values of these variables? If there aren't, then don't measure the ones that couldn't be harmful. I'm struggling to think about how the height of the ear could ever be a harmful effect. Why are we measuring that for the purposes of risk assessment? It might be really useful to know for a plant breeder, for agronomists, but do we really need to know that for risk assessment? This is a Monsanto study by Michael Horak and his colleagues. They're looking at, I think this is Roundup Ready cotton, and they're measuring things like elongation of the cotton fibres. Can you really think of a harmful value of the elongation of the cotton fibre? May be very useful to know for agronomy, for product characterisation, but is this really essential for risk assessment? And if it isn't, I suggest that we ought not to be measuring it, or at least submitting it as part of a regulatory dossier. So the one risk of this is of all this stuff is the cost and time of producing and reviewing the data. That may increase risk. This is a familiar thing. But I think there's also some other interesting things going on here. Measuring these variables, it's sort of like a free hit for those that are arguing that the GM crop poses minimal risk. So if we detect no difference, we can say, well, yeah, this shows that there's the risk of growing the GM crop is no different from growing the non-GM crop. But if we do detect a difference, then we just say, well, that variable's irrelevant for the risk assessment. But it's also extra ammunition for those that are arguing that growing the GM crop is reckless. Look, the elongation of the cotton fibre is different from the non-GM. Think of all the other terrible things that could be happening. So I think by continuing to measure these variables that have no value for risk assessment, we're stoking up controversy. And this is a really interesting paper by Daniel Sarevitz, and he shows how science can make environmental controversies worse. Because what happens is that you just build up a bigger store of data for people with differing views to select from those data to argue their point. And this is why you often get this relationship. And I think measuring these variables that couldn't show any harm, regardless of their value, contributes to this phenomenon. So I want to turn now from things that are irrelevant to things that possibly are relevant, talk about what we mean by plausibility. So which variables could be indicators of harm? And those, I think, are those that are associated with a pathway that could lead to harm. So in deciding what we are going to regard as harmful, we may decide that we want to avoid the loss of species of conservation interest. And we may have come up with a mechanism of that. So, well, perhaps the seed of the GM crop disperses outside the field, the seed overwinters, we get rapid growth of that in the spring, the crop establishes in semi-natural vegetation, displaces the native flora and causes this harmful effect. We could set up a series of testable hypotheses on the basis of this pathway, comparing the GM and the non-GM. So we might say, well, if there's we test this hypothesis that the GM doesn't disperse to a greater extent than the non-GM, there's no greater survival, there's no faster growth, there's no greater establishment, and there's no greater displacement. And this is all predicated on the non-GM not causing this loss of species of conservation interest. So we can compare our GM with something that we have defined as not causing high risk. And maybe this is where some of these data now become useful, perhaps parameters such as plant height, emergence, vigour, the dispersal of the ear and so on. These might allow us to test those hypotheses. So these variables could be used to test the hypotheses outlined previously. So we could test the hypotheses by comparing GM and non-GM isolines, and the hypothesis would be corroborated if the GM was, in quotes, no worse than the non-GM for those variables on that pathway to harm. However, we may have existing knowledge that indicates that one or more of those steps in the pathway is highly unlikely already. So now this sort of situation, so we know that for harm to occur, all the steps in the pathway must be realised together. And if each step is highly unlikely, we know that, knowing that already, then this is the equivalent to several multicoloured swans appearing together. So this is a different point from before. We are saying that if we were to observe a green swan, that would be an indicator of harm. But the likelihood of observing this, especially with all these other things, is so remote that is it really worth looking for them, given what we know about the colours of swans? And if that is the case, then this is what we mean by the pathway being implausible. So an event, or a series of events being implausible, means that the hypothesis that this won't occur is well corroborated by existing data. And what do existing data tell us about the plausibility of harmful unintended effects of transformation in commercial events? As Laura made clear, we're talking about commercial events here. We've assessed and removed a lot the problematic events when we're talking about those which we're considering for commercial release. And we could consider compositional analysis here because Rod Herman, who's in the audience, and his colleagues have done a lot of work on this. It's probably the best reviewed example, and in a paper in Journal of Agriculture and Food Chemistry, Rod says over the past 20 years the FDA found all of the 148 transgenic events they evaluated to be substantially equivalent to their conventional counterparts. The Japanese regulators have found the same thing in 189 submissions. As was pointed out yesterday, these will include stacks. And there's peer-reviewed publications showing the same thing. So I think what we can say is that the hypothesis that transformation does not lead to potentially harmful changes in crop composition is well corroborated. In other words, harm via this route seems to be implausible. So what follows from that? So we've got this hypothesis that transformation event selection does not introduce harmful compositional changes more frequently than do other methods of plant breeding. This has been extensively tested and corroborated. Now, this hypothesis may have been worth testing 20 years ago. It was plausible that harmful changes might result, but we've tested it and found that really it probably is implausible. Do we need to keep testing? Do we need to keep testing it? Is it now implausible that harmful changes might result? There are several other important corollaries that I want to bring out here. That compositional analysis of a specific event also tests the general hypothesis that transformation does not introduce potentially harmful compositional changes. So while our particular study tests hypotheses about our specific event, together they're testing a hypothesis about transformation generally. Follows from that, the case-by-case risk assessment means starting from existing knowledge, not from scratch for each new event. And also, well-corroborated hypotheses are not assumptions. If we choose not to measure compositional analysis, that's not assuming that it's going to be the same. It's basing it on scientific knowledge, a well-corroborated hypothesis that harm will not occur via that route. Finally, I want to turn to this question of weak tests. I think this is slightly difficult to find the right words here, but I think studies with a weak ability to reveal harm itself give little confidence in conclusions of low risk if such effects are observed. And this is really a restatement of the concept of tiered testing. On the other hand, studies with strong ability to reveal the potential for, in other words, indicators of harm, they give high confidence of low risk if such effects are not observed. So in other words, where are you going to go looking for your black swans? Are you going to go to White Swan Lake Provincial Park, or are you going to go to Black Swan Lake? This would be quite a weak test maybe of whether black swans occur. This would be a stronger test. So what we're seeking to do is to do those tests that give us the most confidence that if we don't see the black swan, there really aren't any, rather than just simply racking up loads and loads of observations that really wouldn't have the ability to detect a harmful effect at all. So give some examples. Field studies that look for harmful ecological effects. These are notoriously weak, looking for reduced non-target organism abundance or some ecological function. Perhaps the problems I alluded to before about increased persistence or spread of the crop. These studies are really looking for the harmful effect directly. I think studies that look for indicators of harmful effects are much stronger. So a laboratory ecotoxicology study that doesn't reveal an effect of the active ingredient, I think that is more convincing that the crop poses low risk than perhaps a very underpowered field study. Similarly, with laboratory studies of plant demography. And I think Jörg will talk about this in much more detail this afternoon. So in other words, what I'm saying is we may have this pathway, we've decided what harm is, and we've got this pathway of harm growing from cultivating the GM crop. What I'm saying is the absence of the potential for these events, that ought to carry more weight, be more convincing than the absence of this event itself in a field study. So to give you an example, we've got this pathway that we've discussed before. We've got loss of valued species as the harm, and it occurs by this seed dispersal, establishment and displacement of native flora and so on. We've got our hypotheses. So we could test the potential for these things in our phenotypic analysis field study. Now, if we were to reveal things that suggested that these hypotheses were indeed false, there's a potential for greater dispersal, for example, or there's potential for faster growth, then we could set up some experiments in a glass house, for example, perhaps do some simple competition experiments between the GM crop and some aspect of the native flora. I should say I've never done anything like this, but it's perfectly feasible. This is in contrast to a study that we actually did do, which looked for ecological harm from crop invasiveness in the field. And this was done in Texas, and the idea being that the conditions here simulated those in Mexico, because this was a particular concern that the Mexican regulators had, that particularly BT events would invade habitats in Mexico. So we found a field and we sowed lots of GM events there and their isolines and some land races. We applied pesticides, insecticides and herbicides so that the crop would establish. Then we left it to its own devices. And after a year or so, this is what the field looked like. Perhaps not unsurprisingly, there's lots of scrub vegetation. The only evidence that there was maize there at all were a few cobs and a few stalks. And if you want some data, here they are. So we start off. Here's the crop establishes all right when we're applying pesticides, but very quickly maize simply disappears from this system. After 12 months, we simply didn't observe any live plants. And this illustrates something that often seems to face in risk assessment, particularly I think in risk communication. As a risk assessor, you'll have done something like this. We've worked out what our harm is, and we've got this pathway. We've done our testing, and it suggests that this pathway is not really likely, that it's broken in one or more places. But then people say, well, yeah, this is fine, but it's all a bit reductionist. You're missing something here, and there's this alternative pathway to harm that looks something like this. Something strange is going to happen, something weird happens, and that leads to something bad. And the problem is this really isn't defined. The best you can get is a load of waffle about complex interactions. That's always a good one, or unknown unknowns. Really very undefined pathway. And something bad, well, that usually relates to some aspect of modern agriculture or capitalism or Monsanto, something like that. So really, there's very little as a scientist that you can grab hold of here and test. So I think without a plausible mechanism for harm, testing is inevitably weak. You don't know what you're looking for. You don't know what the conditions would be that would make observation of that phenomenon most likely. So inevitably, it's weak. And I think if you really feel the need to test the hypothesis that nothing weird happens, then I think it's better done as part of risk management, do monitoring if you like, than it is as part of the risk assessment. And there's quite a nice quote here from one of Popper's students, David Miller, and he says, "The aim of the rational agent is not to make the right decision. You may not know what that is, or there may be no such thing. It's to make the decision right." And applying this to risk assessment, I think it really means that we can't eliminate uncertainty. There's always going to be things that you don't know. But do you really need to keep hammering away at the risk assessment, or can you use risk management? If you think something bad might happen, but you can't actually say why, then perhaps it's better done as risk management rather than risk assessment. So to conclude, how do we identify those data that are essential for risk assessment? I think what we're looking for are data that provide strong tests of relevant hypotheses. And for this to pertain, we must define what is harmful. We must define a plausible mechanism by which that harm may occur. The existing data must provide insufficient corroboration of those hypotheses. And the new data that we propose to collect must provide a stronger test than do the existing data. I'd also say that the relevance of a phenomenon for risk assessment doesn't depend on whether it's from an intended or unintended effect of transformation. The real question is this phenomenon essential for harm to occur following the intended use of the GM crop? If it isn't, then it's not relevant. Don't investigate it. If it is, then assess its likelihood by whatever plausible mechanism you think will arise from. If it's going to arise by an unintended effect of the trait, perhaps the BT was the reason that the crop might spread in that field trial, rather than some unintended effect of transformation. It doesn't really matter. What we need to do is to identify the properties, the phenotype of the crop that's going to be important, regardless of the mechanism by which it arose. And if that phenomenon, phenotype, whatever, is not related to harm, then don't look at it. So I think what we ought to be doing is concentrating on relevance and plausibility of hypotheses, the sufficiency of data and the rigor of tests, not whether or not the phenomena are intended or unintended. So I'll leave it there, and thanks for your attention.